This complex subject is very important to power engineers and the general public as a whole. As power engineers should know, the fundamental objective of electric system protection is to provide isolation of a problem area in the power system as quickly as possible, such that as much as possible of the rest of the power system is left to continue service. Obviously, this is highly desirable to both stakeholders, the utility, in addition to its customers. So within this philosophy, there are 5 basic performance principles to consider in order to achieve this desired end. Most protection engineers know these principles as reliability, selectivity, speed of operation, simplicity, and economics. So as such, we have identified 4 key areas where state estimation can potentially provide an important role in improving electric system protection performance. The first area identified is the possibility of increased prevention of protective relay misoperations. This would improve both the reliability and selectivity aspects. Secondly, we have recognized the possibility of increasing the accuracy of fault detection. This would improve, again, both reliability and selectivity. We've also acknowledged the potential to improve reliability of the system by surviving certain equipment failures, mainly like instrument transformers and other sensing devices. And finally, we have also identified the prospects of simplifying the engineering calculations involved, which would tend to reduce the associated human error. Additionally, all of these key areas outlining the importance of our research would play a role in improving the economics of electric system protection due to the improved efficiency involved.
Here we have state estimation as input to protection schemes. So in other words, what we're describing here is the use of state estimations as input to existing relay protective devices with their typical trip setting schemes rather than direct CT or PT measurements. Firstly, it should be recognized that using state estimation as input to protection systems can improve the system reliability by allowing better asset utilization and the use of redundant system measurements. Redundancy naturally improves system reliability. So additionally, this improves the situational awareness of the protective relays and increases the survivability of certain equipment failures, mainly instrument transformers and other sensing devices. This should become more clear when we take a look at our preliminary example on the next slide. But first, let's talk about some applications that could significantly be improved by using state estimation as input. For example, let's first look at motor protection. Thermal overload relays are often used in industrial settings to protect motors from overload conditions. These are typically bimetallic contact devices that separate upon heating due to increased current levels flowing through them. From my experience, these devices pose a significant challenge to the designers of nuclear power plants. You might think that the inline impedance of such devices can be considered negligible. However, they are required to be considered in terminal voltage calculations to ensure that the required motors have adequate terminal voltage in all postulated operating and accident scenarios. And this obviously complicates the calculation process. Additionally, these devices pose a significant threat during degraded grid voltage conditions. Required motors are required to survive degraded grid voltage events in order to keep nuclear plants in a safe condition. This means that all safety-related loads required for postulated design basis accidents must retain the ability to auto transfer to the on-site emergency power supply if the degraded voltage relay monitored buses experience degraded voltage levels sufficient to require separation from the off-site circuit. So these protective devices must not trip prior to the degraded voltage relay timer timeout operation. Obviously, they can then successfully transfer onto the on-site emergency diesel generators. However, motors draw increased current levels when applied with low voltages, which significantly increases the risk of tripping thermal overload relays, which would obviously result in a common failure of equipment throughout the plant. So this is a huge problem in the eyes of the Nuclear Regulatory Commission. Moreover, the NRC likes to cite violations for lack of thermal overload set point testing program, even though there's no industry operating experience to indicate that the set points of these bimetallic contacts drift over time. So a state estimation-based protection could simplify these issues rather than rely on these old-fashioned thermal overload relays. The condition of the insulation in motors can be estimated as a state based on voltage and current draw, which would result in more appropriate protection. Additionally, the state of nuclear equipment could be used as input, such as reactor temperature, allowing the electrical protective system to decide if the motor should die trying to protect the plant, or if it is acceptable to trip the motor offline and protect its internal insulation. And in addition to this, the operability of motor operated valves is a great concern of the NRC as well. Protections of the motor operated valves can be enhanced by incorporating the open or closed state of the valve, by inputting the state of their associated limit switches into the state estimation protection system. And in light of nuclear safety, the overload protection for the motor operated valve can be blocked if the valve did not successfully change states as required. So in addition to this, another example of using state estimation would be increased accuracy of fault detection, which would improve system reliability and selectivity. For example, the real value of current in a fault can more accurately be determined using state estimation. This is assuming, of course, that state estimation can more accurately provide the true system state information rather than direct CT and PT measurements subject to noise and error. A relay subject to input noise, or as seen by the relay, small change in arcing current, say, can cause a large change in arc flash incident energy for protective devices operating in the steep portion of their time current characteristic curves. This is because arc flash incident energy magnitude is affected greatly by arcing duration in addition to arcing current magnitude. So the largest fault current does not necessarily result in the greatest possible arc flash hazard. Therefore, noise could cause arc flash calculations to be inaccurate, and therefore the personal protective equipment selected for the job could be non-conservative. So after those examples, now this is a specific example that we'll be evaluating in detail in our final report. As stated before, observability analysis determines if the received measurements are sufficient to estimate the state of the system. This determines the solvability of the system under state estimation. And although modern PMU and communication technology use is limited, here we are going to assume that all of these economic challenges associated with this are a non-issue. Additionally, we're not going to be addressing the challenges associated with the computational resources required for performing state estimation dynamically in real time for this system. And additionally, we're assuming observability and convergence are not going to be an issue. And although these economic challenges are very important and should not be simply brushed aside, I think it's conceivable that one day in the future, these challenges will be eliminated due to economic growth. And as such here, in this example, we consider a hypothetical 4-bus power system in which all digital components share their electrical power system measurements and perform a nearly instantaneous estimation of the power system states and discard bad data. In such a system, it would be possible for the protective relays to act upon the estimation of power system states and their program settings rather than directly upon CT and PT measurements. And we intend to prove here with this example that this could improve system protection. Several scenarios can be conceived which would perform better than the traditional approach. So we're modeling this system in MATLAB. We will first be simulating a bad data example similar to what was done in homework 3. 5 meters are installed to measure the power flow through each of the lines. And we've started simulating this in MATLAB to identify the bad measurement. And then we're gonna postulate a failed CT and show that it could be possible to survive a failed CT event. Under the traditional approach, this could potentially cause a differential scheme to take an electrical bus offline. But we're going to suppose that this bus supplies critical loads and must be kept energized at all times. So the simulation can be easily accomplished by changing one of the real power measurements to be 0 and rerunning the simulation. And under the scheme that uses state estimation, as we have just discussed, the bus would survive because the bad data associated with the disconnected CT would be discarded, and the protective relay would recognize a more accurate state of the true current in a line. And similar results can be evaluated for saturated CTs.